Good morning to all. Rajna ma'am, I have already shared your presentation. So from my side, I will share, and otherwise, Santosh ji from our NIC team, he will share the presentation. I have also shared this presentation to him also. So first of all, I would like to welcome our additional secretary ma'am, who is kind enough to to accept our request on this very short duration, because yesterday only we finalized in the evening, and she's so kind enough and it shows how much she is interested with the legal methodology, she want to improve the legal methodology system in the country, or the basically the methodology system in the country. Ma'am, I would like to just say 2 or 3 things about the ma'am, as she is working at the CCPA, Chief Commissioner of Consumer Protection Authority, Central Consumer Protection Authority. They have recently come up with the new guidelines for the misleading advertisements. And I'm surprised to say that when I was attending one of the workshop last week on Monday, the people told about these new guidelines uh, published by our department, that this is very good in the interest of consumer, not only in the interest of consumers, for the country. How we are working in a different way, we are trying to do better in the country for the consumer point of view, not only for the consumer point of view, but for the development of the whole system in the country. So I have with us Madam Didi Khare ma'am, and I think the most important step which was taken by this government was the DBT, direct bank transfer. I think this made a revolution in our country, and I am happy to say that today the largest number of the population in our country is using the digital transactions. And I think the credit goes a very few people, including Nidhi Khare ma'am, who have worked in this direct bank transfer scheme in the central government at that time, and made this policy, made this scheme actually happening in the field. And earlier we were not aware that whether this scheme will work or not, because in India, to understand whether this technology of digitalization will work, we think that we will not be in a position to do that. But today we are having the most of the transactions are now being done in the digital form. Even my children, they don't want to carry the money or the cash in their pocket. They say, no, Paytm hai na, hum kar denge wahan se ja karke. So that is the things which we are actually observing in the country, and the credit goes very few people. And somebody told me about some days back, in India, we say that the people are not working. You know why the people are not working? Because we are looking towards those 80% who are actually less working, and we are not looking towards those 20% who are actually working day and night for the development. They are continuously working for the development of the country, technical development, administrative development, and all type of developments, whether it is skills in developing of the people. Ma'am, as you are with us, certainly I always used to say that you are the light behind this whole episode of this national workshops, making a skill development in the country, making the people aware, not only the students of the colleges, not only the industries, not only the state government officers, but anybody who is coming, who wants to understand what is actually science in the country, what is the measurement. And as we are aware, nowadays even the atomic clocks, they are working on these optical science. They want that these electromagnetic waves which can be seen will be very good, and anybody can observe them, anybody can analyze them. With this, ma'am, first of all, I would like to request you kindly inaugurate the workshop. Thank you. Additional secretary ma'am, please.
Good morning, everyone. And I'm really pleased to inaugurate the national workshop on fundamentals of photometry. This workshop, which is being organized for all the stakeholders, including laboratories, industries, the government officers from various state governments, will contribute in actually making the understanding of photometry and the payment and measurement about the subject even more clearly. I understand the importance of photometry in science measurement, and particularly the radiometric and photometric measurements are of importance for a wide range of industries and applications, including the lighting space, semiconductor, photovoltaic, optical communication, automotive, and color industries, displays, and imaging. Other emerging fields include appearance, terahertz applications, photonics, and quantum-based information. Photometry is a science of measuring visible light in units that are weighted according to the sensitivity of the human eye. It's a quantitative science based on a statistical model of human visual response to light. That is our perception to light under carefully controlled conditions. I understand that there are a large number of laboratories in the country involved in optical measurement. I expect that these laboratories are complying with the international standards. The aim of this workshop is to create awareness amongst industries, laboratories, government officers, different regulatory authorities about the fundamental of photometry and radiometry. These types of workshops will certainly help in skill development of technical community of the country and in also developing the quality products of the country, which is the responsibility of all stakeholders in legal metrology. I wish all of you great success in your efforts to not only create awareness, but to also educate the manufacturers, the laboratories, and other stakeholders about the standard methods of testing and calibration and other requirements in the field of photometry. With these words, I would now invite the experts on the subject to actually elucidate about the subject and basically to ensure that in our country also there should be a rising consciousness about quality and quantity both, and any country will actually it will make a difference only when there is a certain consciousness about quality and quantity of their products and services. So with these words, I now open the workshop for discussion. Thank you all. Thank you
Thank
very
you very
much.
much, ma'am. Thank you very much, ma'am. Ma'am, I would like to request you if you kindly speak at least 2 lines about these new guidelines, which will be very beneficial for the participants, because even I don't know what is under these guidelines, which you have just recently notified. Please.
So, as Ashutosh ji has mentioned, the Government of India, through the Central Consumer Protection Authority, which is basically an authority working under the Consumer Protection Act 2019, has come out with guidelines on misleading advertisement, and also, I mean, this is basically prevention of misleading advertisement, and also for the endorsers. So misleading advertisements mean that any advertisements or any claims which are not truthful or which are basically dishonest. Secondly, it could be a guarantee or a claim again, which purportedly promises the consumer uh, about some false say standards about the product, uh, which actually contributes to the unfair trade practice, which means that you are selling something, saying, for example, a particular apparatus is going to correct your vision, but actually the product does not or is not capable of actually correcting your vision. So this is something which is unfair because not only it is false and misleading, it also is essentially cheating on other products in the market which are truthful about their products. So in that sense, it is unfair. Then it is also, if you conceal very important uh, information, which should be known to the consumer, then this is also misleading. For example, if you purchase, say, some food item, and you are also using a lot of coloring agents, some of which may be carcinogenic, and you do not inform the consumer about what is, because this is very, very important. So concealing such important information from the consumer who is consuming this product, and which can lead to say tumorous growth or some other forms of cancers, this is also misleading. And it is for the first time that in the country today we have a guidelines on such misleading advertisements. These guidelines also they also they are going to affect the endorsers, which means those people who are celebrities or who are influencers on media or who are influencers on the social media. So you find, very young people who are unemployed, who have absolutely no idea about the product, neither do they care. But because they have on the social media about 1 lakh followers, then the company is also using their, say, level of influence to market their product. And if they do not take due diligence while endorsing any product, then they can also be liable uh, under the um, under the act, and therefore they can also be penalized. It's for the first time that not only the manufacturers, the advertising agencies, advertisers, and even the publication of such advertising material, and also as well as the endorsers, all would be liable if any such misleading advertisements are found. Now, I just wanted to also conclude by saying that we have already taken action, for example, against a very prominent tele-shopping like Naptol, who was basically selling, gold ornaments for 200 rupees. And when we asked them why they are, when it is not gold, why have they named their product as, gold ornaments or gold jewelry? So they said that since the price itself is so low, they thought that the consumer would be wise enough to understand that it cannot be gold. So this was found to be an absolutely, a fit case for misleading advertisements. So they were penalized and they were directed to discontinue with such advertisements. They were also using, a pre-recorded material, which basically told the consumers that, say, for example, only 2 bed sheets are left, or only 2 products are left, or only 5 products are left. And if you do not purchase, then it will go out of stock, or some such thing. But the consumer who was watching these things did not know that it was a pre-recorded message. He thought that this is, in time, something which, so again, he was being taken for a ride. And this was an unfair trade practice against which they were penalized. And a penalty of 10 lakhs was imposed on them. And they have also not only discontinued those advertisements, they have also deposited the penalty. Similarly, there's another brand, a very popular brand, which was actually using not only an unethical thing, but it was also making very tall claims that their toothpaste was being recommended by the dentists worldwide, or that it was the world's number one, dentist recommended, toothpaste. So again, we found that this is, they were also using, Indian doctors, but practicing in UK for their endorsements. Now, in India, there is a code which basically prohibits dentists or medical practitioners from endorsing any commercial product. But they were trying to circumvent this code by employing those who were Indian doctors or dentists who were practicing abroad, or who who were not, who were not registered with the Council of the dentists, the dental surgeons. But this again, was found to be a misleading advertisement, because sometimes when the experts make endorsements, for example, a medical practitioner or a dentist, then the consumer thinks that this must be, a prescription. It is taken more as a prescriptive kind of a product. So again, it is unfair on the consumer. We penalize them with a fine of 10 lakhs and ask them to discontinue all those ads. They have discontinued all those ads, and they have also now deposited 10 lakhs rupees. Under the guidelines, any subsequent, episode of misleading advertisement can invite penalty up to 50 lakhs. Or, and the same is true for the endorsers also. So I'll be very happy if, the audience here is also become a little vigilant, becomes more aware and looks for, this kind of trend amongst our manufacturers and people, I mean, the traders who basically mislead consumers, also try to claim unsubstantiated accounts for the product, and they then try to basically cheat and defraud the consumer. So I'll be very happy to hear from you all. You can, in case you find any such violation, you can approach 1915, which is the National Consumer Helpline. And otherwise, you can also, through e-Dakhil, can lodge a complaint at any of the district or state or national consumer commissions. Or you can, in case you find that this requires, and this is a befitting example of a class action, then you can also approach CCPA. So I'll be very happy to hear from all of you. And we need to be vigilant. We need to, as consumers, try to make, a safer, a much more truthful and honest depiction when it comes to advertising. So with these words, I think I have already spoken and
Thank
taken
you
a
very
lot
much.
of time.
Thank you.
Thank you.
Thank you very much, ma'am. No, ma'am. It is also very much required to understand what are the new things which are coming up. And these misleading advertisements are not only the problem of today. These are last 70 years which we were facing since long. कि ये क्रीम लगाइए गोरे हो जाएंगे, ये दवाई खाइए लंबे हो जाएंगे. So these type of things we were facing since long. And I think it is very good that at least some authority has started taking action. It is very good. Today, ma'am, we have with us Professor Rajana Mahratra, who is the head of the physics National Physical Laboratory from India, and she has done her PhD from IIT Delhi in 1980s. She is since last more than 30 years. She was in NPL. She has recently retired from NPL. She has done a lot of work in radiometry, spectrometry. Whole of the life she has spent in this field. So I thought that I will not find a person better than her. So I just requested her. Yesterday she was in our office, one of the BIS meeting, and I was not aware of that. When I called her, she was just going back, so I could not met her yesterday. But
But
today,
I didn't meet you. Did I?
ma'am, your mic is off. Rajna, ma'am, your mic is off.
Okay, just a minute. I was very much there, ma'am.
Uh,
I was very much there. I am the chairman of ET23.
Acha, so you were behind the mask.
Actually, we were in the mask, so you couldn't recognize. I
All
was very much
right.
there. Yeah.
Okay, so you were the chairman of that committee.
Yes, ma'am. I
In
am the
fact,
chairman.
in fact, I was thinking that in my inauguration note also, I must mention that. But since you are here, I think nothing like it. You can also tell the people how, people are fighting about, they are resisting standards making.
Actually, ma'am, it is very unfortunate. We have been trying from last 1 year for publication of this standard, but the industry people are making very hue and cry. Ma'am, some of
Exactly.
the industry people are ready, but
Yeah,
this Alcoma side is they are not ready at all.
I know.
And I feel very, I'm very sorry to say that they use unparliamentary language in the meeting. I have
Ah,
high objections to that. And I have
yeah, yeah.
requested BIS to at least read the code of conduct before starting of every meeting in BIS.
Bilkul, bilkul. That's how it should be. But I
Ji,
think you must have also appreciated that while,
I know, ma'am.
our secretary,
Yeah. He was so much, he
he was
handled the
such a
meeting
support.
so well. Yes, ma'am.
Yeah.
I just came out and I told Ashutosh ji that he was of so much of help. and he
Ah.
really turned so politely
He turned
and
the
so
tables
nicely.
on these
Yes,
people.
yes,
You know,
ma'am.
they had no basis to, their argument had no legs to stand on,
Ma'am,
frankly.
they are selling the same thing, 25,000 hours to US and other countries. What
Uh,
happens if it is in India?
mm,
Because those things are also manufactured in India only when they are exporting.
yeah, yeah, yeah. And see, the thing is that they did not, if you have an issue, you are saying that the same product will not work in India because of its very, peculiar or unique situation. Then why was the industry shying away from carrying out experiments and, back up with support, support of the facts? So where
Ma'am,
were the facts? They were not willing to conduct
yeah,
testing at their level.
yes, ma'am.
They were trying to stall whatever standard making has been done on the scientific, ground by the BIS or by your committee for no
Yes,
good reason. Just because they occupy 35% of the industry doesn't mean
yes,
that they have a right to
yes,
kind
ma'am.
of monopolize.
Yes, ma'am. No, actually, ma'am, from last 1 year, we have been telling them that let's publish this IS and simultaneously do some experiment. And
True.
after 8 months, whenever your results are out, okay, so we will just make some amendment in that. But they are not ready for that. We
Yes.
have already minted that, but they are just
Mm.
not ready. They are just going, making complaints and going higher ups and higher
Ah.
ups.
No,
They will go to
I think
court.
Secretary was, sir was very, very he understood the whole subject very
Yes,
clearly. He also understood, why what they are doing. It was
yes,
completely unscientific.
yes, ma'am. Yes, sir, we could make our we were just talking outside that how beautifully he handled the situation.
Yes, ma'am.
Yeah.
She told me
Very,
this the same
very,
thing.
yeah. Yes, ma'am. Thank
Thank
you
you,
So
so much, ma'am.
good to see you then. Yeah.
Thank you,
ma'am.
ma'am.
Ma'am, additional secretary ma'am is always with us to support for the
Thank
betterment of
you.
the
Yes,
country.
I could see that. I could see that. She was there. I could see
Yes,
her. Yeah, ma'am. Thank you so
thank
much,
you.
ma'am.
Sir, ma'am, we have our director, Shri Biyantishi Saab also with us. I will request to director Saab to speak kindly 2 words so that we can start then immediately after the presentation. Please, sir. Dikshit, sir.
Uh, Ashutosh, this is the wonderful discussion regarding photometry and its advantage and all those type of things. So, photometry is one way related with the velocity also there. And one things I will like to inform you whether you might be aware or not, sir. Uh, Earlier, there were the two-point balances, high accuracy balances. They were based on the photometry. Okay, and these balances still are available at our Indian Institute of Legal Metrology. So they are used for the micro measurement at 10 kg weights, and that we can say that our one of the oldest items in our uh, Indian Institute of Legal Metrology. I think that that type things may be available at the National Physical Laboratory also, because that is the highest laboratory, and they are also maintaining such type of the standards and balances. Maybe with the modern times they have the latest things, so they might have kept somewhere, but they were using those type of things. So the photometry plays the lot of the important role in the science, and it relates with the velocity measurement. Uh, when you talk about the sunlight and its velocity and all that with things, from there everything is started the things on that very thing. So uh, it was the observation from the Einstein times. Then this photometallurgy developed, and now it has developed in all the fields, and its uses are in the many fields of science, even biochemistry, biology. Uh, Physics is the important things where the photometry is being used. So we have the expert madam from NPL. So I respect her, and I have heard her many times, and I hope that we'll be fortunate that to hear her speech on today workshop, and it will give the knowledge to uh, all of us who are part of this workshop. So with these very words, I give lot of thanks to you, Madam Nidhi Khare, Additional Secretary, and Dr. from National Physical Laboratory, and your team. Thank you.
Thank you very much, sir. So I would like to just a very brief introduction of Ma'am Rajana Malhotra, who has more than 40 years of experience in the field of infrared and Raman spectroscopy, photometry, and radiometry. She is now the professor in Sharda University since 2020 after getting superannuation from National Physical Laboratory. She has published more than 150 research papers in the reputed national and the international journals. He has done a lot of supervision of students for the PhD. She is also coordinating the number of courses in National Academic Research Center. She is basically the life member of many professional societies and the committees of BIS, International, and etc. Ma'am Rajna Mehta, I would like to request you to kindly share your presentation and let us make us also aware about the new technologies which are coming up in the field. Please, ma'am. Thank you. Thank you very much, ma'am.
Thank you, Ashutosh ji. First of all, I would like to thank Mr. Ashutosh Agrawal sir for inviting me to give this talk. I'm really thankful to Madam Nidhi. And yesterday's also, I was really impressed by her, the way she tackled the situation. And I'm really thankful to you, ma'am. I'm thankful to Dr. Dikshit also. So I will just like to start, and I'll request Mr. Santosh to share the presentation because there's some problem and I'm not able to share it. So I request Mr. Santosh to share the presentation. Mr. Santosh, please. You have to turn the slides also. I'm sorry for that.
No problem, ma'am. He is basically the backbone of the department in the this computer and all problems.
Okay. Yeah. So I'm going to speak about the fundamentals of photometry. And we all know that the photometry base unit is candela. And actually, I have made this talk very, very basic because as Mr. Agrawal told me that most of the people will be who will be really working on the floor. So I just want to tell that some basics about it, because the photometry is not a physical phenomena. Photometry is basically a physiological phenomena. So I would like to tell about the science of eye, because it is a physiological phenomena. What we perceive, that is the photometry. And then I would like to go for how the measurements are done and how the uncertainties are calculated. So I have tried to assemble everything and I will try to make everything in 1.5 hours, which is the time given to me. I will just try to see how best I could do. So this is the spectra, which is the optical portion of electromagnetic radiation. And the visual light is very, very small portion. One side is the ultraviolet and other side is the infrared in this electromagnetic spectra. You can see in this electromagnetic spectra, I have started from radio waves to gamma rays. I have spoken waves and rays. There are two words I have spoken. I did not say radio rays. I said radio waves. Why I have spoken, I will just tell you in the next slide. Next slide, please. Yeah. So this is the ultraviolet, and we know that ultraviolet is also very, very important in lighting, because most of the light has little bit of ultraviolet portion. Ultraviolet is basically very useful for germs killing, and it's very dangerous for our eye. That's why I have just shown that ultraviolet, CIE is defined ultraviolet in 3 parts: UVC, UVB, and UVA, and it can cause the skin disease also, and these things has to be kept in mind to all the manufacturers. So I have, that's why the reason I am showing this particular slides. I'd like to go to the next slide, please. Yeah. So now I tell you that I said one side ray and other side waves because the light has the dual nature. The physical optics, and there are 3 kinds of light is divided into three subfields. One is the physical optics. The physical optics is study the wave nature of the light. Then comes the geometrical optics. This is study the particle nature of the light. So some of the phenomena in optics can be explained using the wave nature. Some of the phenomena can be explained by the particle nature. And then comes the quantum optics. This has the dual wave and particle nature. So all the phenomena can be explained by the quantum optics. So basically light is a stream of photons, the quantum of the electromagnetic radiation, the property of electromagnetic wave and the property of the particle. So the E is equal to h and nu. H is the Planck's constant, where nu is the frequency. This is basically the equation in quantum optics, which solves all the quantum physics, quantum optics, which solves all the dual nature. It can explain all the phenomena of dual nature, and E is equal to P into C, where P is the momentum of the photon and C is the speed of light. And Dixit sir also said just now that it is the speed of light. C is the velocity, speed of light basically in vacuum. E is equal to P into C. So there are 3 main property of the lights. One is the intensity, or alternatively it can be said amplitude, which is related to the brightness of the light. That is the intensity. Other phenomena is the frequency, or it can be said wavelength. This is perceived by the human as a color of the light. And the third is the polarization. This is angle of vibration, which is only weakly perceptive by the human under the ordinary circumstances. So we are not going to speak here about the polarization. So basically we are interested in, basically we are interested in, basically we are interested in intensity and frequency here. Next slide, sir. Yeah, so there are few phenomena. I will give you few of the definitions. So the first definition is, this is reflection, which is very common. We all know, actually what I'm going to tell you, you all must have you all know it, but I'm just brushing it up just to remind you to go further for the when we discuss about the measurement. The reflection is a process whereby light of a specific wavelength incident on a material is at least partially propagated outward by the material without changing its wavelength. So you can see that there is a surface, the source of light is falling on that, and then it is getting reflected. So the incident angle is equal to the angle of reflection. This is law of reflection. This is also called law of reflection. The incident angle is equal to the angle of reflection. The next slide says the transmittance. When there is an incident being falling on any sample, it gets absorbed, certain amount of intensity of the light gets absorbed, and then certain amount comes out of it. So the transmittance is the fraction of incident light at a specified wavelength that passes through the sample. Okay, so the transmittance is denoted by T and can be written by I upon I0, the light which comes out of the sample, and the light which gets incident beam, the intensity of the incident beam. So T is equal to I upon I0, or transmittance can also be written in terms of absorbance. Absorbance is then log 1 upon T, or log of I0 by I, that is absorbance. The sample is there, the light is falling on that, it gets absorbed. So that is absorbance, or the light which is transmitted after getting absorbance, that is transmittance, and the definition of the absorbance. Now, next slide, please. Yeah, there are different type of transmittance. Specular transmittance. Okay, I have also made how it is falling and getting transmitted. I have also depicted it by the figure. The specular transmission causes light to propagate without any scattering, as it is clear glass. So in the glass, when light is falling, there is no scattering. It is assumed that there is no scattering, and most of the light is getting transmitted. Now the diffuse transmitted, when the light falls on a surface like false glass, it gets diffused. Okay, it goes in all the direction. You can see the figure which I have shown there, that is diffuse transmission. The light goes from the top and it gets diffused. Then the mix in the normal day-to-day life, what we get is the mixed transmission, where the light is not purely specularly transmitted, not diffusely transmitted. It is basically the mixed type of transmission, in which this is the weighted combination of specular and diffuse transmission. So these are different kind of transmission basically which takes place when we talk about the light. The next slide. The next slide talk about the reflection and refraction. There are two words, reflection and refraction. When a light wave rays travel from one medium to the another, part of the incident light is reflected and the part of the light is transmitted at the boundary between the two medium. Now you can see the first figure. There is at the 60 degree, there is one light is coming, and then there is air and the water medium. The light is coming at the 60 degree, and the 60 degree, because the law of the refraction is there, reflection. So 60 degree it is coming, I is equal to R, and then it is going back. And then the light is passing from one media to the another media. Okay, from air to the water, so it is getting the refracted ray. Okay, so the reflection, there is a difference in the reflection and refraction. Okay, so the light is reflected back, and when it goes from one media to another, it is refracted. Okay, so you can see another figure that at 60% light goes at angle of 60% when a beam goes to one surface of air and glass surface, 60% comes back. At a 60% angle, 60 degree angle, it will come back, and 35.3 degree angle, it is refracted in a glass surface when it is an air and glass surface. So this, so you can understand the reflection and refraction in this particular slide. The next slide says, there is a law known as Snell's law. So in general, when light enters a new medium, its direction will change. The angle of refraction is related to the angle of incident. Not necessarily that 60 degrees, so there will be 34.5, which I have shown in the last slide and previous slide. It is given by the Snell's law. It is sine theta 1 by V1 is equal to sine theta 2 by V2. And this is a constant all the time, where V is the velocity of light in the medium. So the velocity of light in air will be different, velocity of light in glass will be different. So Snell's law says that n1 sine theta 1 is equal to n2 sine theta 2. The angle theta 1 and theta 2 are measured relative to the line normal to the surface between the two medium. N is equal to C into V. Okay. So this is basically the Snell's law. These are all taught in, I think, 10th standard, 8th or 10th standard. Now I go to the another slide. It is just, I'm just brushing it up. Reflection is also very different kind of reflections. Now we talk about reflection. Now there are different kind of reflections. One is called the specular reflection. This is specular reflection is that light is falling on that and is totally getting reflected. Specular reflection is, for example, is from mirror. Okay, when a refraction causes light propagate without any scattering, that is specular reflection. Diffuse reflection is the light get diffused in with equal energy in all the sides. But in day-to-day life, what we see is the mixed refraction, which is again the weighted, as is in transmittance, it is again weighted reflection of combination of specular and the diffuse reflector. Most of the surface exhibit complex reflection, vary with incident and reflected direction. You can see specular, diffuse, and specular plus diffuse is equal to total reflectance. Okay, that is the mixed reflectance, which is the specular reflectance and the diffuse reflectance. Now I can show you some of the examples which all lighting industries are making. You can see the specular reflectance. Now this is the diffuse reflectance. Many times you use the diffuser. And in real life, you can see the specular component and as well as the diffuse component. Okay, when light falls on any surface, it totally depends on what kind of surface it is a surface phenomena. Okay, yes, please, next slide. Now there is another word, diffraction. Diffraction is another phenomena that depends on the wavelength. So when light wave bend, when light passes through the narrow aperture on a slit, it bends. It bends when they passes through the edges of a narrow aperture. If theta is the diffraction angle, so theta is equal to lambda by d, where lambda is the wavelength. Okay, so it basically depends on lambda, and lambda means wavelength, means different colors. When we talk about visibility, it is different colors, right? The effect is explored in monochromator. When we use the monochromator for measurement, we basically see this effect, diffraction. Okay, next slide, please. Now comes interference. Light waves also display constructive and destructive interference like sound waves. So waves that are in phase, if you can see the example A, the waves are in the phase. So this is called constructive interference. The first and the second wave, the amplitude of the wave at a particular wavelength get added up. This is constructive interference. When the waves are not in phase, like one deep is coming up with other up, right? So waves that are half a wavelength out of phase, interference is the destructive interference, and in this you will find a straight line as a resultant. So these are the interferences. You see these type of things when we work in lighting industry. We need we measure or we come across diffraction, interference, and all this. Okay, unless and until you know the basics, we're not able to do the best, right? Let's go back to the next slide, please. Now the diffusion. We know that you might be using diffusers at many places. It is often necessary to diffuse light, okay, either through transmission or reflection. So the diffuse transmission, like you put it, it gets out and it gets diffused. So it is the phenomena in the lux meter. I've been telling you because we use lux meter all the time. So we know there the phenomena of diffuse transmission is there. Okay. And then diffuse reflectance is the luminance measurement. When we do the luminance measurement, we need to know the luminance, the diffuse reflectance, this phenomena takes place. So I have been telling you all these things because finally you will be using lux meter, luminance measurement and all. So these are the phenomena. You should know that these phenomena are used for lux meter and luminance meter. So it is very necessary to know all these definitions or brush up all these definitions again and again. Next slide, please. Now, what is total flux? Most of the slides I have put the figures so that it is very easy for us to understand. So as I said that photometry is a physiological phenomena, we can't measure it. What we can measure is the radiometric parameter, that is flux. Total flux, we can measure the flux. We can measure the angular intensity. So the flux is the light emitted in all the direction. That is flux. The angular intensity is the light emitted in a specified direction and angle. That is intensity. Basically, intensity is the light emitted in a specified direction with the angle is the intensity. Flux is the light emitted in all the direction. That is flux. Next slide will tell you. Now, the radiometry, basically what I just said, radiometry is the measurement of optical radiation. Right? Okay, again I am showing you that electromagnetic radiation figure. Basically, radiometry is the optical radiation, but photometry is the physiological phenomena. It is the measurement of light which is electromagnetic radiation detectable by human eye. जो हम देख सकते हैं, that is the photometry. And this is the range which I have given, 380 nanometer to 780 nanometer or 390 nanometer to 70, which we can really see. That is the photometry works there. So this is the sensitivity of human eye. I'm going to speak about it in long run. This is a sensitivity of human line which is already defined by international bodies. So any measurement which we do, radiometric measurement, because we can only measure the power, the radiometric parameter, then we have to weight that radiometric parameter with our human eye response. And then only we can calculate the photometric parameter. Okay, so next slide. Yes. Now the technique in radiometry, that is the energy measurement. What we measure, how much energy is produced. That is a radiometric quantity. How much energy is produced? It is radiometric quantity or a radiant. And photometry is how does it looks to human. And that human, how does it look? We have to weight this parameter with our human eye response to get a photometric parameter. The quantity start with photopic or luminous. When we talk about luminous, it means what we can see. Okay. So first we measure the radiometric parameter, then we convert it to the photometric parameter. The next slide. And then one more word comes, spectroradiometry. The spectroradiometry tells us that how is the energy distributed. Means spectra, where the word spectral comes, it means how the energy is with particular wavelength. Like which color. The wavelength means again the color, which color. Right? The spectroradiometry is how is the energy distributed with the wavelength. That is the spectroradiometry. Okay, next slide. Yeah. In photometry, all the radiometric quantity are weighted through V lambda. That V lambda is the response of the eye, which correspond to the sensitivity of the human eye. A human eye sensitivity is also different in light, daylight and night light, which I will come later. So first let us define here radiant flux. Radiant flux is radiant power emitted by a source, energy per unit time through observable area. Okay, that is radiant flux. And in photometry, that is luminous flux. When the radiant flux is weighted by V lambda, that comes the luminex flux. The irradiance, radiant power that falls per unit area, that is irradiance. And here, when it is weighted by V lambda, it is illuminance. Then radiant existence, that is radiant power emitted from unit area. Here it is luminous existence. The radiant intensity, radiant power emitted to solid angle. Now I will show you how the solid angle and all. Luminous intensity, these words you might be very much familiar. Luminous intensity, this is our base unit, this is candela. Okay, and radiance is luminance. And I have also written the units of it. Okay, so what we do, we measure the radiometric parameter and then we convert it to the photometric parameter. Next slide. Now, before 1940, it was only the visual comparison, whether it's more intensity, more flux, or it was only the visual comparison. Now the modern photometry with photometers available, the relative spectral responsibility of human eye need to be defined. So after 1940, it was thought that human eye response should be defined. So they collected many human people and then they have taken the observations and then it was defined based on that. In radiometry, the detector has a flat surface response, but in photometry, the spectral response used to visualize a system is considered. What our eye can see, the photometry, the response, spectral response should be photometry, spectral response should be human eye response. So the detector which we use in photometry, that has to be closely matched to the spectral response curve of our eye. As I said, it is a physiological phenomena. So photometry is little difficult because it is not a physical phenomena. It is basically a physiological phenomena. So it has become little difficult than other measurements. Please, next slide, please. This is basically human eye color vision. The human eye visual system can detect the range of light spectrum for 400 nanometer or 380 nanometer to 700 nanometer. The following illustration show the visual spectrum approximately as a typical human eye experience. So you can see that 400 we see little violet and 700 see red, infrared. So UV comes the one side, 400, below 400, this is UV, and above 700 nanometer in wavelength, this is infrared. The next slide will give you, yeah. Now let's understand the human eye. Why some people can see the color some other way and some see the color some other way. That all depend on our human eye structure. So let us understand a little bit about eye, because whenever you talk about photometry, the eye automatically come into the picture. The eye basically is secured by 6 muscles. I basically take more interest in this because I am basically a biophysics person. So I would like to explain it in detail. Now the sclera is the dense white, you can see the white portion in our eye, that is called sclera, is a dense white fibrous material, except where it becomes the transparent corona, cornea. You can see that there is a white portion we can see in our eye. Okay, and you can see in this picture also. And then there is a cornea, which is a transparent gel-like substance fill in the eye. This is called vitreous humor. You need not to go in these biological terms, but we should know the function of eye. An elastic lens is situated. अभी जब old हो जाते हैं तो हमारा basically lens change होता है. जब cataract हो जाता है, that is this elastic lens which is situated in the vitreous humerus and cerebella by a muscle, right? So basically what जब वो हो जाता है हम लोगों को यूजली ज़्यादा एज में आपको लेंस चेंज कराना पड़ता है because lens becomes foggy and there are many other reasons. So this is the lens, elastic lens. The lens shape is controlled by the muscle action to the focus the image. The lens is very important for focusing the image. Light passes through the cornea, lens, and vitreous humor. Okay, you can see that because I'm not in person, so I can't put light on this, but you can see that how the images fall, where it gets focused on back wall or fovea. Okay, so I go to the next slide. Yeah, the inner wall of the eye is covered with a layer of light sensing cells. Now, this is very important. The inner wall of the eye is covered with a layer of the light sensing cells. So, retina, the nerve fiber perturbing from each cell from complex web network, eventually forming the optical nerve. The retina contains 120 million photosensitive receptors. That's very important. That is why we can see the color. The retina contains 120 million photosensitive receptors, that is called rods and cones. The cones are concentrated in the fovea and they're responsible for color vision. So why we have color vision? Because the cones are sensitive for color. अब many people, actually when we go for any government job, अग्रवाल साहब का भी हुआ होगा, any government job, we have to go for eye testing, and we have to go for color sensing. Many people are color blind. Their cones are very less in number, or it's not there. So they can't see, they can't distinguish between the color. If there is a red, they may read orange. So there are very few cones available, so they can't see. Some people are totally color blind. They can only see black and white. They can't see at all any color. So government job, it is very, very necessary that you pass through this, that you can see all the colors properly. So we have to go through, we went through rather, all this color measurement. So there are several millions cone available in average in one human eye. The cones are not present in fovea, but populated other area in the retina. The information created in rods is funneled out through the optical nerves to the brain, and then the optical nerves are there that gives the information to our brain, and then brain immediately respond which color it is. Can we go to the next slide? Yeah, you can see these are the rods which are big, and the smalls are the cones. There are three types of cones. You can see in the right hand side of the presentation, rods are there, and then green cones, red cones, and blue. So we have basically red RBG system. Okay, now down you can see the nerve fiber, light goes there, then the rods are there and the cones are there. So some people don't have cones, so they are colorblind, and some people have less amount of cones, so they can't see the color properly. Okay, so these are the cones which are responsible for color vision, and then there are rods which gives us the black and white. We can go to the next slide, please. Now, our eye have three sets of sensors. These are basically sensors. No, what is the best detector on the earth is our eye. Eye is our best detector on the earth. Our eye have three sets of sensors which peak sensitivity at the frequencies called red cells. These are 680 nanometers, green 540 nanometers, and blue 450 nanometers. Light at any wavelength in the visual spectra range from 400 to 700 nanometer will excite only one or more of these type of sensors. So when the light falls on our eye, any of these things gets excited. If they are there, then only it will get excited. If we don't have cones, it will not get excited, right? Our perception of which color we are seeing is determined by which combination of sensors are excited, by how much. It is customary to denote RGB sensors with the Greek letter rho, gamma, and beta. You can see beta, you can blue, gamma, green, and rho is red. So this is the customary. I have taken it from the website. So this is basically the customary to see. Next slide. Yeah, you can, this is another thing. This is in the daylight. The sensitivity of the curve of rho, gamma, beta sensor in our eye determines the intensity of the color we perceive from each of the wavelength in the visual spectrum. The following illustration is an approximation of the visual spectrum illustrated, adjusted for the sensitivity curve of rho, gamma, and beta. Okay, this I have taken from CIE. Okay, next slide. And this is in the dark. The human visual system has much greater sensitivity in low ambient illumination. The cones contributes little. If it is a dark in the night, the cone contributes little and no sensitivity in this condition, or sometimes there is no sensitivity. This image is accomplished by rods when illumination level is very, very low. The plot that follows shows the spectral sensitivity of the rod. When the illumination level is 0.001 candela per meter square, we can only see, अभी रात में आप देखेंगे कि आपको हर चीज कलर नहीं महसूस होता, एक परछाई लगती है डार्क और आई मीन वाइट एंड ब्लैक जैसा एक परछाई सा दिखता है रात को बहुत अंधेरे में. उस टाइम हमारे कोन सेंसिटिव नहीं हो पाते हैं क्योंकि लाइट बहुत कम होता है, तो हमारे रॉड सेंसिटिव होते हैं. सो व्हाट वी कैन सी इज दिस. ओके, सो नेक्स्ट स्लाइड. या, now when we go old, aging is a human eye. I'm just telling you just for interest. Aging of human eye is a natural process. It involves loss of accommodation of focusing capability because lens ठीक से काम नहीं करता तो focusing capacity नहीं होती. This reduces, because it reduces the pupil size छोटा हो जाता है, thus reducing the amount of light entering the eye. Older people requires extra lighting. The thickening of the optical lens, absorbing more light and scattering it. Image and less contrast and sharpness. बहुत लोगों को sharpness cataract हो जाता है तो बहुत sharp नहीं दिखता, blur दिखता है. 20 years old eye can receive 6 times more light than 80 years old one in bright conditions and 16 times more light in dark conditions, right? Good lighting can make the difference between seeing and not seeing for the older adults. So when we talk about older adults, so we have to put the more intensity of the light over there. So the next slide, please. Yeah, so spectral response. Now let's come back to the spectral response. Human eye is more sensitive in some wavelength than to the other. Human eye contains two types of photoreceptors, cone and rods. Cone are responsible for light adopted vision, and they respond to the color. Cones are basically for color, C and C, cones for color. And when the eye is adopted for the bright light, it is called photopic vision. Okay, and the cones dominates, and the luminance level greater than 3 candela per meter square. If it is 3 candela per meter square, cone R starts working, and this particular vision is called photopic vision. And illuminance level below 0.001 candela per meter square, the rods are more dominant, and it is called scotopic vision. But there is something in between also, and people have never thought of it, but a lot of work is going on these days. In between, both rods and cone contributes in varying amount, and this range And in this range, this vision is called mesopic vision, and a lot of countries have started working on mesopic vision, but so far no the standard body has not taken this thing into the consideration. A lot of research is going on, and after some few years, I think we will have a mesopic vision also. So we have a photopic vision, we have a scotopic vision. We have two kind of visions. Okay. Please, next slide, please. Yeah. So this is CII photopic and scotopic sensitivity curve. So the photopic sensitive curve is active at 555 nanometer. Photopic peak 1 watt is equal to, at this particular 1 watt is equal to 683 lumen. Photopic vision, and the scotopic vision, it is at 5112. The next slide will show. Next slide, yes. And when I have done that, what I have done that I have, this is the photopic and mesopic and scotopic vision. And when I did the Gaussian function, we have found that V lambda is equal to 1.019 e raised to the power minus 285.4 lambda minus 0.559 square. This is V lambda Gaussian function for photopic vision, and this is Gaussian function for scotopic vision. This is basically done by doing the Gaussian distribution, seeing the Gaussian distribution and fitting it, the given curve, fitting it to this equation. So if we use this equation, these two equations, we can find the Gaussian curve for photopic and scotopic vision. Okay, next slide. Yeah, these are basically the values. I have shown you the curve. Now you can see the values. Which lambda, what is the value? Okay, so these values are given. You can refer to this, or you can find it in any of the book of lighting industry. Yeah. So the photopic vision eye sensitivity V5, if we defined luminous flux here, so the luminous flux basically is equal to 683 lumen per watt into integral of phi e V lambda d lambda. V lambda is the photopic vision eye sensitivity. Okay, when we talk about photopic vision, of what we can measure phi e. We can measure the luminous flux. We can measure the radiometric flux, and then we can weight it by V lambda factor, and at 555 nanometer, this is equal to 683 lumen per watt. So if we, so this way the lumen flux can be calculated. What we measure is lumen, is radiant flux, and then we multiply it by V lambda, weight it by V lambda, multiply it at sensitivity of human eye at 555 nanometer for photopic vision. Similarly, we can calculate for scotopic vision. So this formula can be used to calculate the luminance flux. I think you all might be using it in your day-to-day life if you are working in a lighting industry. Next slide, please. Yeah, now let's show how the origin of candela. So prior to 1948, it was how the definition of candela has changed. So prior to 1948, the definition was the candle power. This is the brightness of a flame from a standard candle. This candle is still there in the museum in UK. Brightness of the flame from a standard candle of defined composition, or the brightness of an incandescent filament of specific design. That is candle power. So prior to 1949, this was the definition. It was the candle power. In 1948, it was defined as a new candela, and the brightness of the full radiator at a temperature of solidification of platinum in 60 new candela per square centimeter. This is the definition of new candela, which was given in 1948. New candle, sorry. Then in 1967, candela is defined. This is the luminous intensity in the perpendicular direction of a surface of 1 upon 600,000 square meter of a black body at a temperature of freezing platinum under a pressure of 101,325 nanometer Newton per square meter. This was the definition given in 1967 based on black body. Because of difficulty in realizing a Planck radiator at high temperature, the new possibility offered by radiometry in 1979, modern definition of candela was adopted. So in 1979, a new definition of candela has come, which I am coming to that. And 683 nanometer has come while calculating all these things. Next slide, please. Sorry, I'm doing it myself, trying to do it. Yes. So the candela basically is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 into 10 to the power 12 hertz, which is at 555 nanometer, because it's the photopeak peak, and that has a radiant intensity in the direction of 1 upon 163 watt per steradian. Okay. In other words, lambda is equal to 555 nanometer and the radiant intensity is 1 upon 683 watt per steradian. Then the luminance intensity is 1 candela. Okay, so 1 candela, basically, now this is the definition on which we are working on. So this is the definition. I think I am running slow, so I should run fast. Next slide, please. Yeah. Now solid angle, basically the solid angle is a 3-dimension equivalent to the 2-dimension angle. And the solid angle is a measure of steradian. I talk about steradian. I just want to explain. This is basically in 2-dimension, it is called angle, and 3-dimension, it is called steradian. Okay, angle is equal to length by radius, and the solid angle basically is area by radius square. Okay. Next figure will show you, probably give you a better perception of solid angle, please. Yeah, you can see there is a sphere. It is a 3-dimension, and if we cut a fraction of that, this is basically the solid angle, right? This is area by r square. Okay, you can see the area, you can see the r. So it is now the luminous flux, basically it is given in lumen. And what is luminous flux? I have made all the illustration. I'll go very fast because you all must be knowing it, but I just want to brush it up, and this illustration will make you very clear what it is. Luminous flux, this is the radiant flux multiplied by relative spectral sensitivity of human visual system. And you can see that this is the property of the source. Yeah, radiant flux, basically what we measure the radiant flux and then we convert it to the lumen flux. So I have already said radiant flux phi is equal to del Q by del T. Q is the energy, basically. Okay, this is optical power or radiant power, and it is unit in watt. And the luminous power, when we multiply it by km, km basically is the 555 पे आपको क्या फोटोपिक विजन है या स्कोपेटिक विजन है, तो यहाँ पे km की वो वैल्यू आएगी. देन E phi is the same thing. This E is basically energy, and V lambda is basically the human response of the eye. So the radiant flux we measure and convert it to the luminous flux. Okay, please, next slide. This is illuminance. How much light falls on the surface is illuminance. Illuminance flux density at a surface. It means illuminance flux incident per unit area. Per unit area पे क्या light पड़ेगी, that is illuminance flux. Luminous flux. Okay, let's go to the next slide. Let's go fast little. Irradiance and illuminance. Irradiance is the density of incident radiant flux at a point on the surface. watt per meter square. You can see by the figures. And illuminance, again, you have to weight it. Okay, then you get the illuminance. Next slide, please. Now, there is a law. The irradiance is a measure of radiometric flux per unit area, right? Or flux density. Irradiance is typically expressed by watt per square centimeter or watt per square meter. Illuminance is a measure of photometric flux per unit area or a visual flux density is typically expressed in lux, lumen per square meter, lux, or foot candela. These days, no one uses foot candela. It is the lux, expressed in terms of lux. So if there is, for example, the illuminance decreases, obviously the illuminance will decrease as we go far, right? So the illuminance decreases from 1 lumen per square feet at a distance of 1 foot to 0.929 lumen per square feet, 1 lux at a distance of 3.28 feet. So the illuminance will decrease as we go far. Okay, I wanted to show you in this slide. Next slide, please. Now comes the luminance. Luminance intensity of a light source is relation to the emitted light of a emitter. Okay, light source or a reflecting area. Okay, next slide. Now similarly, this is the radiance and luminance. So you can read it also. I go to the next slide. It is the similar way as I told you. Now, luminance intensity. The luminance intensity is calculated by luminous flux emitted per solid angle unit to a specific direction. So basically we find out the luminous intensity, and it can be calculated by luminous flux emitted per solid angle unit to a specific direction. That is the luminous flux, luminous intensity. Okay, so basically what we measure is the luminance intensity and the flux and all other parameters as well. Next slide, please. Now the radiant intensity we calculate and similarly find out the luminous intensity. And you can, if you go through it, you can understand it's very easy. If it is the isotropic source, I will tell you in the next slide, please. Yeah, now there are two words, lumen efficacy and lumen and efficiency. The efficacy is the ability of radiant energy to produce visual sensation, which is measured in lumen per watt of emitted light. This is characterizes the radiation spectra rather than the source. So basically, K is equal to luminous flux upon K, जो luminous efficacy कहलाती है, that is luminous flux upon radiant flux, that is efficacy, luminous efficacy. And the efficiency कहलाती है, measured in the lumen per watt, is the ability to light source to consume electric power into the visual power. It's not necessary that all the consumed power is converted to the visual power. Very little portion of consumed electric power is converted to the visual power. Luminous flux. Okay, so luminous efficiency is equal to phi V upon power. So these things, I think you must be using it. So remember, please, next slide. Isotopic source. Now we should have an isotopic source. It means the source which is spreading light in all the direction equally. Phi is equal to 4 pi L. Okay, phi or intensity is equal to phi upon 4 pi. It's radiating in all the direction equally. That is called any source which is any point source which is irradiating equally in all direction is called isotopic point source. Okay, next slide. Now, there are two laws, inverse square law, and it is very common sense. Inverse square law, EV is equal to IV upon D square. जैसे जैसे हम डिस्टेंस में आगे बढ़ेंगे हमारी जो इंटेंसिटी कम होती जाएगी. तो 0.5 EV is illuminance, IV is the intensity and D is the distance. Like D comes in the denominator. Okay, so the intensity will decrease because D is in denominator. The distance जैसे जैसे हम जाते जाएंगे हमारा जो है कम होता जाएगा intensity. That is inverse square law. Okay, the next thing is cosine law, Lambert cosine law. The irradiance of illuminance falling on any surface varies as a cosine of the incident light. Like it is cosine 0 is 1, so E theta is equal to E, 100%, you can see. Then it is 30, then 87%. If the theta is 60 degree, it is 50%. If the theta is 85 degree, it is 9%. So if the light source is on the top, the maximum light will fall on the state direction when it is cos theta, theta is 0. Okay, this is cosine law. Next slide, please. Yeah, Lambert surface, emission and reflection. A Lambert surface reflects or emits equal flux in every direction. For example, an evenly illuminated diffuse flat surface. So this is basically required when we talk about integrating sphere and all. We want to know a equal diffusing surface. Okay, like a piece of paper is approximately Lamberian surface or perfectly matte surface. Radiation depends on the angle of incident and not on viewing direction. Okay, so next slide. Now we talk about the color temperature. An object to any temperature above 650 K will produce a spectrum emission with its color related to the temperature. We know all about color temperature. The color progresses from a very deep red through orange, yellow, white, finally bluish white. This path is plotted on a chromatic diagram and is known as Planckian locus. Most natural light sources such as sun, star and firefall are close to this locus of the point. So the daylight fluorescent lamp is 6500 K. आप लोग use करते होंगे. Daylight source and CRT computer display is approximately 6500. The next slide will tell you more about that. Yeah, then comes the correlated color temperature. It is defined as the absolute temperature, expressed in Kelvin, of the theoretical black body whose chromosity most nearly resembles with its light sources. Okay, so you all must be knowing about CRT, and I have already given daylight and no light. You must be knowing better than me because you have been working कि कौन सा सोर्स बना रहे हैं, कैसे कौन सा डेलाइट सोर्स है, 5500 के है, 2700 के है, स्टैंडर्ड इनकेसिडेंट लैम्प है वो 2700 के पे होता है, हाई प्रेशर लैम्प 2200 के एंड ऑल. So you know about correlated color temperature, but just go through it. I have shared my presentation with Ashutosh sir, and you can share, he can share with all of you if you want. Please, next slide. So these are again this warm white light and neutral light and daylight. You can see all these things, and I think you all know about it. Next slide will. I just want to tell you one of the measurement. Color rendering index. CRD is the capacity of artificial light source to render the color of illuminated objects as compared. As compared to the daylight of the same color temperature. So this is color CRT, and CRT more than 90 is excellent, and I mean you can just read it about it. I just want to go to the measurement. One measurement I just want to show you. Please sir, next slide. Yeah, so these are the how the civilization came and how we reached from it was a torch initially, and then it came to the candle, and then it came to the Edison bulb in 1879, and then how it has developed. The next slide will show you. Now it's the time of LED. Now, next slide, sir. These are the way and how much is the we have gone from past to the now. And next slide will show that this is the time of the LED. And LED photometry is entirely different photometry than the photometry of the lamps and CFL and TFL and GLS. So this is the way you can see that how the luminous efficacy is going high, and how now it is from 2000 onward, and now we are 2022, and now it is all LED, and maybe after some time these all are redundant and we only give focus to the LED, and LED photometry is entirely different. If I have been given the chance, I can speak about the LED photometry as well. Please, next slide. Yeah, I would like to show you this lamp. This is basically a lamp, which is a standard lamp. Must be having, all of you must be having this lamp. This is a standard lamp. And I'm especially attached to this, showing this slide, because 2 times I have taken these lamps to other NMIs, especially PTB Germany, and got it calibrated. Did the calibration myself too, because 2 labs has to make the calibration equal, then only the trading can be done, right? So this is that. The next slide will show you the spectral irradiance lamp. Yeah, this is the spectral irradiance lamp which I have taken to PTB Germany for calibration. So this is spectral irradiance, and these all lamps are available with all the NMIs. NMI, just India NMI is National Physical Laboratory. So these standard lamps are available there. Next slide, please. Yeah, this is the example of luminous level. Next slide, you can just go through it. Next slide, please. This is the example of luminous level. Okay. So how much light do we need? This is very important. How much light? So the orientation and simple visual task, we can have 30 to 100 lux. The common visual task, the commercial, industrial, and residential application, we need 300 to 1000 lux. And special visual tasks, including those with very small and very low contrast critical elements, we need 3000 to 10,000 lux, lumen per meter square. Okay, so this is how much light we need. A common man should know how much light should be needed. Next slide, please. Yeah, so we know for trading and all, we should have 2 NMIs should have the same measurement, same capability, measurement capability, and same measurement. If my value is the same with the value which people sitting in Europe has, then only we can sell the things, otherwise we cannot. So for doing that, we should have the same measurement, we should follow the same procedure, we should follow the same measurement. And CII has published the international standardized human visual response, which establishes basis of photometry, and then we have Indian standards as well, many times adopted by abroad, many times written by Indian BIS. And next slide, please. Yeah, this is the response which I've already shown you at 555 nanometer. The eye sensitivity is maximum 555. This is taken from ZIE. They have also defined the same. The next is this is photopic vision. Next is yeah, this is the dark vision. This is maximum is 512. The next, please. Yeah. Now we come to the luminance intensity, and we know that luminance intensity IV is equal to d5 by dw. Just a minute. हेलो, संजय, मैं एक टॉक में हूँ, थोड़ी देर में बात करती हूँ आपसे. The equivalent definition of luminance intensity is derived from illuminance, which is shown in the figure, and you can find out EV is equal to d5 by dA, or is equal to IV by R square. Okay, so based on this, we will be doing the measurement. Next, please. Yeah, this is basically the experimental setup for luminous intensity. So you might be having a small bench, but when you go to the big NMI like PTB Germany, they have 500 meter or 1000 meter long benches they have. The huge hall is there for intensity as an intensity bench. Okay, so we have a black background, then we have to have a source here, and then we can read it at particular distance to a silicon photodiode. And this silicon photodiode is specially designed for photometric measurement. So it is weighted by V lambda curve. Okay, so the V lambda curve is V lambda filter is also there on the on the silicon diode. A V lambda filter is put over there. So the measurement, this is basically a very simple measurement setup, but the measurement has to be done very, very precisely and accurately. See the filament, and where the geometry has to be very, very has to be adjusted very well. And these are the baffles. These baffles are put here so that the reflected light or the diffuse light doesn't fall on the photodetector, because the photodetector is a very sensitive. So it can read any light which is coming from all the sides. So it has to be done in a totally dark room, and it has to be covered by total dark cloth or some other material. So basically, this is a setup for luminance intensity measurement. Next slide, please. So the intensity represents the flux flowing on the source in a given direction per solid angle, that is used to quantify the power of the light source. As definition implies, luminance intensity measurement involves several geometrical factors such as measurement direction, the amount of solid angle. So the light source are rarely homogeneous, so many things has to be taken into account, or they contribute to the uncertainty. Next slide, please. Hence, to measure the luminance intensity of light source meaningfully and aged the agreed upon friction that defined the solid angle in compressed with the measurement and are orients, and that orients the light source repeatable in an specific direction must be used. Solid angle can be calculated from the known detector area and measurement distance. Detector is used to measure the flux reading in the lumen. So first we have to use the flux reading. Here, next slide. And the lumen flux measurement is determined the total visual energy emitted by the source is flux. So for this, the integrating sphere is often used to convert the power emitted by the source to the detector head. And the integrating sphere, and then again you can use the goniophotometer, but the goniophotometer is basically not used for measuring the day-to-day sources because it's a very expensive affair. So and goniophotometer basically the lamp moves around the detector so that the light in all the direction can be calculated. The integrating sphere, this has to be large enough to encompass the light source being measured, and in general rule, the larger the shape, larger the size and shape, the smaller the error in measuring the luminance for different light sources. Next slide. This is basically the flux measurement by goniophotometer, and you can see that the light source is put in between and the photometric head is moving. In some cases, you can see, I'm sorry, I spoke in hurry, I spoke the wrong way. The source is put on at one particular direction fixed, and the photometer head is moving in all the direction and 360-degree, and calculating the flux at all the point, and then it is integrated to get you the total flux. The next slide is the integrating sphere. As far as so the integrating sphere, next slide is basically the integrating sphere. So you all must be knowing it. And the coating of integrating sphere is basically done by different chemicals. BaSO4 is one of that. BaSO4 is very good diffuser, and the intensity diffusing reflectance, it should be a flat reflectance. Matlab, it should diffuse from all the direction equally. So the Teflon is the best, but integrating sphere with the Teflon is very, very expensive. So basically, usually people keep BaSO coating. They do the coating of BaSO4. So that gives the flat this thing. Yeah, next slide. So now the uncertainty measurement, I just leave these things because I think the time is getting out. So will you please leave these things? These are the uncertainty. I go to next slide where the A or B type uncertainty is given. Yes. So this slide also you can just read it, nothing much. Next slide, please. Yeah. So there are different kind of uncertainty. When we calculate the uncertainty, the parameter associated with the result of measurement that characterize the dispersion of the value that could be attributed to the measurement in the uncertainty of the measurement. Dispersion of the values that could be attributed to the measure and is the uncertainty of the measurement. There is standard uncertainty. This is the result of the measurement expressed as a standard deviation. Now the type A measurement, this method of evaluation of uncertainty by the statistical analysis of series of observation. So there are different type of uncertainty, type A uncertainty, type B uncertainty, and then comes the combined uncertainty. The type B uncertainty, type A uncertainty is the measurement uncertainty. We do the measurement 10 times or 20 times. This is a statistical method. How many times, how many number you increase, your uncertainty is going to reduce. Okay, so this is basically based on the statistical variance. You have to find out the variance, standard deviation and variance. And the second is type B uncertainty. This uncertainty method of evaluation uncertainty by means other than the statistical analysis of series of observations. I will tell you what type B uncertainties and in luminous intensity, what all comes into the picture. The combined uncertainty of the result of a measurement when the results is obtained from the value of the number of other quantities equal to the positive square root of some of the terms, variance or covariance. I'll explain you further. Next slide. Leave this slide as well. Yeah. Random error and symmetric error, you can read about it. Okay, I just go further. I go further. Yeah, the result of a measurement after correction of recognized systematic effect is still only an estimate of the value of the measurement because the uncertainty arises from random effect or from imperfect correlation. The following may be the source of uncertainty. Now, the source of uncertainty, these are the source of can be the source of uncertainty: incomplete definition of measurement, imperfect realization of definition of measurement, non-representative sampling. If the sampling is not done properly, the sample measured may not represent the defined measurement, and inadequate knowledge of effect of environmental condition. Many times in the environmental conditions makes a lot of difference. Personal bias in the reading the instruments, finite instrument resolution. Sometimes the resolution of instrument is not there, or discrimination their threshold, inexact value of measurement standard and the reference material, inexact value of constant and other parameters, approximation and assumptions incorporated, variation in repeated observations. These may be the cause of some of the uncertainties. So we have to be very, very careful that these should not happen when we are doing the measurement. Next slide. Now, type A and type B measurement, both type of evaluation are based on probability distribution and uncertainty component resulting from either type are quantified by variation or standard deviation. A-type uncertainty is obtained for a probability density function derived from an observed frequency distribution, and B-type standard uncertainty is obtained from an assumed probability distribution function based on the degree of belief that an event will occur. Matlab, A-type of uncertainty is what you measure, and B-type of uncertainty, what the uncertainty can be in all other things which are involved in the measurement. Okay, that comes with your experience, that comes the uncertainty which is already there in the instrument which are used, and many other factors. Yeah, please, next slide, please. Now, the probability and probability distribution to associate a measure with the likelihood of the outcome of an event is a question. In question is called probability of the event. If the, okay, I will read it. If the trial has n distributable, mutual, exclusive outcome, which are equally likely to occur, and if n out of these capital N possible outcome have an attribute or character that we call as sequence or success, then the probability of success any one trial is n minus n. ये तो probability में पढ़ाई है हमने. These are various property of probability, union, subtraction, and many more, which we are not going to discuss it over here. So basically, there are certain probability distribution, and we have to work on that. Next slide. If all the quantities on which the result of the measurement depends are varied, its uncertainty can be evaluated by statistical means. However, there is a rarely possibility in practice due to limited time and resources. Therefore, usually the uncertainty of measurement is evaluated using a mathematical model of the measurement and the law of propagation of uncertainty. The mathematical model may be incomplete, so that the relevant quantity should be varied to fullness. Practicable. I think you can read all these things. I go to how to calculate it further. These are the practical consideration. I go to further. Next slide. Yeah. So the A type of uncertainty is the measurement which we take. Okay, the flux measurement or the intensity measurement which we have done, A type. Now the B type of measurement, for an estimate xi of an input capital Xi, there has not been obtained from repeated observations. The associated estimated variance U2xi or the standard uncertainty is evaluated by specific judgment based on all the available information on the possible variability in capital Xi. The pool of the information may be include previous measurement data. The B type of uncertainty comes from the previous measured data, experience with or general knowledge of the behavior and the property of the relevant material and the instrument, manufacturer, supplier specifications. You know, in measurement of one equipment, there are so many other equipments are used. So the other equipment uncertainties are there, which are cause of the type B uncertainty, which will be taken into account of the type B uncertainty. Data provided in the calibration and other certificates, because the other instrument which we'll be using for measuring this will also have some uncertainty. So those uncertainty will come as a B type of uncertainty. Uncertainty assigned to reference data taken from the handbooks, that is also given in plus and minus. So those uncertainties will be taken into B type of uncertainty. Okay. So next, this is again the setup which I've already shown, the measurement. Now we 2 slides will show you how to calculate. Please, next slide. Now, for uncertainty in the lamp, illuminance at the detector surface, distance of the detector from the lamp source R, spectral responsibility of the detector S lambda, the amplifier gain of the detector G, the geometrical factor. These are all comes under in uncertainty, B type of uncertainty. In the substitution calibration lamp of the similar shape, size, rating, and has some operating color temperature, the spectral responsibility of the detector, the gain of the amplifier, and geometrical factor do not contribute much to the uncertainty. Okay, it means that these are the B type of uncertainty. But if because we use the substitution method, we measure the test sample and then we measure the reference sample. So because it's a substitution method, So on substitution also done by the same shape, size, rating, and the same operating color temperature. The spectral responsibility of the detector, the gain of the amplifier, and the geometric factor, these will not contribute because we are taking everything is the same, 1-to-1. If there is a 1-to-1, then there is a comparison. Okay, so the intensity of a reference standard source can be written as I is equal to ES into R square. Next slide. Yeah. Similarly, the test lamp written IT is equal to ET into R square. 1 and 2, we can calculate the test by the IS standard into ER into R square, RT square upon ES into RS square. And then now we know that IT, basically what becomes? It becomes a function of IS, ER, ES, RT, and RS. Since the measurement of I is in terms of product of the input quantity, the relative combination variation can be given as uncertainty U square IR by IT, and you can see that this formula can be used. Okay, because it's a function of this and it has come in the multiple. See, you can see it is a multiplication. So we can write this equation in this form. The next slide. Now the output quantity IR is the product. Again, the combined uncertainty can be expressed in this form. And the relative combined variation for IT, it can be written in this form. If you can go one by one, you can understand it. Okay, please, next slide. Now, consider the case. Now, let's consider the case when the luminance intensity standard use has a certificate value of 128. Now, the standard we have used, uska certificate value is 128 plus minus 1.4 candela. The illuminance ES produced by the standard lab at a distance of 2 meters is equal to 32.2 lux. And the illuminance ET produced by the test lamp at a distance 2 meter is 2.001 meter is 33.61x. The value of IT of the test lamp can be obtained by putting IS and other factors IT, and you can find out this is IT is equal to 133.61 candela. Okay, we use 2 meters here. We could use 2.001 meter the square, and then we have the test lamp, and then we had it is the same formula which I have shown it before. Okay, the next slide. And this is the measurement which we have done. Now we have done 10 measurements. The value is this. The average has come out to be this. So we can calculate the standard deviation. This is the way to calculate the standard deviation. This is the A type of uncertainty. Please, next slide. So the A type of uncertainty, when we calculate the standard deviation, the A side of uncertainty has come out to be this much. The value of the uncertainty, relative uncertainty, is given by this. The degree of freedom is 9. And when we do the 10 measurement, the degree of freedom is always 9, n minus 1. This comes n minus 1 because when we know the last value, the added value, and we know the rest 9 value. When we know what is the added value and what is the 9 value, the 10th value can be calculated. So the degree of freedom, we have only 9. We don't have the 10 degree of freedom. Right? Because 10th value can always be determined if we know the total value and we know the 9 value. If we substitute the 9 values, add 9 values and substitute, the 10th value can always be known. So we can find out the degree of freedom is 9, n minus 1 always. It is never n. Next slide. Similarly, the relative uncertainty for this can be evaluated by type A. All other for type A, for 9, degree of freedom 9, we can calculate all the values. Next slide. Similarly, yeah. Or now the B type of uncertainty. Now this is very important. B type of uncertainty. Long-term drift of reference photometer between recalibration uncertainty. Degree of freedom is infinity. Sir, previous slide. Sir, previous slide. Sir, next slide. Yes. So these are the B type of uncertainty. This is very important. The long-term drift of reference photometer between the recalibration, photometer temperature variation. Okay. Another uncertainty, spectral mismatch of the lamp. This is another uncertainty, lamp. And these uncertainty, it can come with the experience. It can be taken from any reference. Okay. And the lamp current regulation, it can be read from the test lamps. This is lamp current regulation, lamp current measurement uncertainty, how you are measuring the lamp current. This is that stray light uncertainty. This can come through your experience, the random noise. Okay, so these are all B type of uncertainty, and you can also think of some more B type uncertainty. That depends, that comes from your experience, right? So these are all B type uncertainty. First, we calculated A type, did different measurement, did the standard deviation and the variance, and then we did the B type uncertainty. Some values we have taken from the standard uncertainty, which are given in the leaflets. Next slide. So now the combined relative uncertainty can be calculated. Okay. Next slide. Now we find out the degree of the freedom. Now this is the formula for calculating the degree of the freedom. So we have taken some of the degree of freedom were the infinity, which we have taken, some degree of freedom were 9, which we calculated, right? So we find degree of freedom is infinity. For confidence level 95 and degree of freedom infinity, the coverage factor is 2. This we can see from the table which is given. Expanded uncertainty with coverage factor k is equal to 2 is 1.84 candela. The statement of the result, now how much we will find, therefore the value of IT is equal to 1.33.61 plus minus 1.84 candela. So this is our the statement of result. Okay, this is the way to find out the degree of the freedom. Next slide, please. Now this way we can find out the luminous flux also. The uncertainty in luminous flux can also be found out the similar way. I think now I would like to thank you. I have taken more time than I was given. Yeah, this is a luminous flux measurement, and I think you can go through it. I have already shared my slide. Thank you, Santoshji. Thank you, sir. Actually, I have exceeded time. I'm sorry for that.
No, ma'am. Thank you very much, ma'am. Thank you very much for your kind presentation. Actually, we have given you the complete time for 1.5 hours, and you have explained in a very well manner. Actually, you know, since long, even I forgot most of the definitions. I was even just taking my notes. What are the new things I am learning from today's presentation? It was very good, and
No.
certainly we are thankful to you for your great
Thank you,
presentation
sir.
and help us help
Actually,
our
because you told me that this will be attended mostly by the people who are working on the floor.
Yes.
So I tried to make the presentation as common, because of this basic things are very, very important. Because and I try to make it by showing by the figures, so that actual real feel can be,
Yes.
can be felt.
But it is very good, which we come to know that in PTP Germany, they have 5 kilometer long or 1 kilometer long.
Yes,
slippage.
they're such a big. I was astonished to see that, you know.
Okay, and it is in Berlin or
No, sir, it's not in Berlin. It is in Braunschweig.
Acha, Braunschweig. Because most of these facilities they are having at Braunschweig. Some of the mass and
No,
others.
the light is basically the optical is in Braunschweig.
Okay, I have seen. I remember one time I went to UK and this NMO legal methodology UK. They were having big test bench of water meter. No, sorry, not water meter, length measure. I think it was about 100 meters like that. This much long test bench, and
And
they're having.
suppose, sir, it is a dark room with 1 kilometer long, and yeah. And
Yes,
there's nothing, but they have kept side by side many things for measurement. So
yes.
because all the
Actually,
time, you know, intensity measurement is not taking place.
Yes, and secondly, they actually they are working in a different way. One person who is working at one field, he is actually the master of one field.
यस सर, यस सर,
This is
यहाँ
it.
तो मैन पावर की बहुत शॉर्टेज है ना सर.
And we should say that we have abundant manpower.
यस सर, यस सर,
Large number of maximum manpower we have. But ma'am,
यस.
thank you very much. Thank you for your kind support. And
I'm
certainly,
also really thankful to you, and I'll be I mean, I have no problems in if anyone wants to go in detail,
oh,
I
very
can
good,
do
very good.
that.
Next time we will be having one presentation for the industries, how the industries have to manufacture it.
Okay, I have no issue. You can tell me before, sometimes before in advance, so
Sure,
I can
sure,
prepare well,
sure, ma'am. Sure.
prepare
Thank you
the
very much.
slides well. Thank
Thank
you.
you.
Thank you very
Thank you,
much.
ma'am. I would like to thank my additional secretary, ma'am, director sahab, and all the NIC team who is here to support the whole program and all the participants who have attended this. Thank you very much. Thank you.
Thank
Thank you,
you,
ma'am.
sir. Thank you. Thank you.
Thank you.